Welcome everybody, good afternoon and welcome to this webinar. I'm Steve Holliday, I'm the President of the Energy Institute and delighted to welcome you to this webinar. We've got a great panel of experts here this afternoon to talk about a subject that is increasingly, I think, on the lips of many people, and that's hydrogen. So let me just give you a bit of administration details of how this will work. Each speaker is going to give a short presentation, and then we're going to open up for a panel discussion and a Q&A session. So our plan is to finish this at 3:30, so we've got 90 minutes. The session's actually being recorded, and the recording will be sent out by email after the event's ended. If you've got a question at any stage during the course of these proceedings, then please just use the chat panel to type in your question. If it is aimed at any particular individual, if at the end of the question you could just say this one is for X or something, that will be helpful. And then we'll sift the questions and we'll come back through them. But hopefully we're going to have a lot of good questions. And as I say, you can put those questions on at any time. Let me just introduce, for those of you who may not be fully familiar with the Energy Institute. The Energy Institute is the body which for chartered professional membership, bringing together expertise to tackle the two challenges that we're constantly talking about. That's the challenge of getting access to energy on a global basis, and at the same time, managing the challenges of climate change. It's a unique independent network spanning the complete world of energy, convenes and facilitates debate, and gives voice to issues of concern. And when necessary as an institute, we challenge the industry who, of course, we work with very closely. It aims to be where energy professionals are and where they're headed. So why, understandably, we continue to support those who work and manage the production of conventional fuels, particularly focusing on the safety and efficiency in that industry. The climate emergency also means that we've been pivoting our activities towards the new technologies that will reduce greenhouse gas emissions as quickly as possible. Whenever I talk about the Institute, I talk about the fact that today it's pretty much 50-50. It's 50% what you might refer to as the old energy industries and 50% all the new industries. Carbon capture and storage, networks, offshore wind, onshore wind, battery storage, and of course what we're talking about today, hydrogen. So in order just to frame our discussions today on hydrogen, it's pretty clear that the science says if we're to get anywhere near what the Paris Accord was, then net zero has to be hit between 2050 and 2070. And it's astounding, and I think, and one of the pleasing things, just how quickly that language of net zero has got into our vocabulary. I mean, I meet people all the time who talk about net zero, which a year or so ago just wouldn't have been the case. 80 countries now have committed to net zero by 2050. And of course, our government moved really quickly. So the Climate Change Act 2008 very quickly actually modified for net zero. And quite clear from our government, a huge amount of attention on it, given that we're hosting COP26 in November next year. I think if I stand back and think about what net zero means, it's for me, in talking to energy consumers, all of a sudden put a focus on the fact that everyone's involved. When we were 80%, I think there were an awful lot of people who thought they were in the 20%, who it wasn't really going to apply to. We've really got attention now. There is no hiding place. And there's no hiding place, therefore, in terms of solutions either, which means that we absolutely need to use all technologies. And one of my frustrations, certainly when I was the CEO of National Grid, in an era when for 10 years it was all about facilitation of clean and new energy, there were always advocates for a different technology. Everyone arguing that they were the solution to the issue. I think it's pretty clear with net zero, we need all technologies. And yes, electricity is going to be a huge enabler of our net zero economy, but I think hydrogen is a massive second enabler, both as a store for energy and of course as a carrier for energy. And it's increasingly now identified, I think, and being seen by people as a big response to the emergency that we actually face. Yet again, though, I get a bit frustrated when I hear people saying the answer is hydrogen, as if everything else doesn't matter anymore. It's the only answer. So this balance between a recognition that we need all technologies, for me, is incredibly important. But there's no doubt in my mind that hydrogen, if we can produce it cleanly, is going to be a huge part of our energy future. But there are some big challenges to overcome. Safety, clearly, affordability. How much can we actually produce in a low carbon way? Some of those are the issues that our panelists will actually explore today. Before I introduce the panel of experts that we actually have, we've issued today, the Energy Institute have just issued an essential guide to hydrogen, intended to be quite simple in a sense, and demystify and put some facts out there for all walks of life, really. I think for politicians, for schools, for teachers, etc. This is available as an online resource. What you see in front of you right now is a screenshot of the web page. It's hosted on the Energy Institute Knowledge Services. And the guide explores a number of key questions. It explores what is hydrogen, how it's made, how it's moved, how it's stored, how it's used. Why does it matter? So the importance of it in tackling our climate change and air pollution. How does it compare? So how does it compare in terms of practicality, cost, the safety issues I was mentioning? And what's it going to be like? What's it going to be like for people who use it in homes, in vehicles, or in businesses? You can put the next slide up. Interesting, you don't have to read the whole guide either. So it's set out if someone wants to go in and interrogate it and just answer one of the questions, then they can. So there's a detailed section here, for instance, on hydrogen in the home or transport, as I mentioned. Next slide. We've got some really good graphics in here. I know in testing it with a few people that they've enjoyed that. They found that it's engaging, quite easy to read. All the jargon, because inevitably there is some jargon and some technical terms, are all in a glossary as well. So you can hover over those and get it and get a definition. Next slide. And there's some maps. So when as we're going to be talking today, you'll certainly hear from Adam about the project in the north that's going on here. So you can hover over the map and get more details on each of these projects. So that's gone out today. I hope it's going to be helpful as hydrogen becomes more and more part of the policy in the UK, an easy guide to people starting to understand the opportunity and some of the issues that are there. So it's free to download as a PDF. So please do share it amongst your networks, pass the links around. I'm certainly optimistic it's going to help more people start to talk about hydrogen and demystify some of the bad information that, of course, is inevitably already out there, I suspect. So let me introduce your panel for today. We have Jennifer Baxter, who's the head of engineering at IMechE. Adam Maggot, I mentioned just now, who's the project manager for High Deploy that Northern Gas Networks are building. Chris Jackson, who's the director of PH1 Alstom. 4 experts in their own field, each going to talk about various aspects of hydrogen. And as I said, if you've got a question during any of these talks, please put it into the chat and we'll pick it up. Just tell us who it's aimed at, if it's someone in particular, or if it's just for the whole panel, and I will sift through them as we go through. So without further ado, let me hand over to Jennifer Baxter. Good afternoon, Jennifer, and over to you.
Thanks, Steve. Hello, everybody, and thank you for having me this afternoon. As mentioned, I'm Jen Baxter. I'm the Chief Engineer at the Institution of Mechanical Engineers. And just for some context, I wrote my PhD in the sustainable production of hydrogen about 10 years ago. And so it's been really interesting to see the developments that have happened over the years, and particularly probably within the last 3 to 5 years. So this is just a brief presentation, a whistle-stop tour through the overview and sustainability and user experience of hydrogen. And I am making some assumptions here that everybody knows what hydrogen is in the first place. So just to say that the first thing that I want to talk about here is that the Institution of Mechanical Engineers produced an energy hierarchy just over 10 years ago now. It's recently been updated, but it basically follows the same elements here. And the reason for this is that often in electricity, we talk about energy conservation and wasteful behavior, but we don't talk about it so much around gases or fuel use. So we want to make sure that this is talked about across all elements of energy. And so when we talk about it in terms of hydrogen, what does this mean? It means that ideally you get to produce less hydrogen, which means that you need fewer plants, fewer sites, and that more opportunities for smaller entrepreneurs to feed into the hydrogen system. So this is an important element of when we consider building a hydrogen system, that we should also look at how we're using it and how we can reduce that use. So you can go to the IMechE website and have a look at that document if you should wish to. So this is just a quick slide that gives you some ideas around the production methods for alternative fuels, and I tend to work around most alternative fuels, so this is just one of my slides. And hydrogen is very similar in some ways to biomethane in the way that it can be produced, particularly if you're looking at it directly in gas form. But when you're talking about producing it from electrolysis, it also adds opportunities around renewables with electrolysis and nuclear power with electrolysis. And a kind of fun fact around nuclear and electrolysis is that if you produce hydrogen this way, you are using both the heaviest and the lightest elements that are found on Earth for your energy generation system. So that's kind of interesting. And then just looking on the other side of the slide here, it just identifies how gases, both methane and hydrogen, can be used across our energy system. But in addition to that, you can also look at how it can be used in industry, as we use a fair amount of hydrogen in industry as well. Another area I want to draw attention to, and I'll talk a little bit more about later on, is on the sustainability side. So using our existing assets in terms of sustainability means that we are actually making sure we are maximizing the use of the resources that are put into those assets. We're maximizing the skills that have been developed, the money that has been put in, and the way in which those systems connect to our wider infrastructure that already exists. So making sure we continue to use it is a really big part of sustainability. So just moving forward here a bit to where I think that we may start to see hydrogen used in wider systems. I know that people are familiar with the idea of hydrogen produced from wind or solar power, and as I've just mentioned, from nuclear power. But I think as we look into the future, it's likely that we will see different and much more mixed systems. So mixed gas production, biomethane, synthetic methane, and hydrogen being produced together in the same sites. Electricity and gas systems, so power to X. So this is where we use electricity to produce a gas like hydrogen through electrolysis, or you can use it to produce a liquid as well. So for fuels too, so synthetic jet fuel, for example. District heating and mixed gas fuel cell systems. So I'm not specifying which gas these fuel cells could come from, but hydrogen is an option, but there are other gases that can create fuel cells as well. And cogeneration, power, heat, and gas. So again, nuclear power is a really good option here for how you bring together different parts of the energy system to produce power, to produce heat, and also then to go on to produce hydrogen as well. So I've borrowed a couple of slides in this presentation from my colleague Chris Jackson from Protium. It's a different Chris Jackson to the one on the panel, also working in hydrogen, just to add a little bit of confusion. And this just identifies how the different parts of the system could work. So enabling the renewable energy system, so enabling large scale renewables, distribution of energy across sectors and regions, and then looking at how it can act as a buffer for increased resilience within our electricity and energy systems. And then there's the decarbonising the end uses, so transport, energy use, building, heating and power, and also serving as feedstocks, as we mentioned previously in industry. And I think this is an important factor which I'll come back to again, because it starts to help us to identify how we can begin to build a hydrogen economy. So looking at the sustainability angle, now we don't talk about this so much when we talk about hydrogen, or actually even when we talk about renewables, because it's often goes with some kind of assumption that new cleaner technologies are automatically sustainable or green, and that isn't actually always the case. So I wanted to just draw some attention to parts of the hydrogen system that really do meet some good sustainability criteria. So one of the good things about hydrogen is that it can be produced in the UK using low carbon electricity. You can create a system here where you really don't need much input from anywhere else. We've got wind, we've got water, we've got all of the things that we need for this system. It can be produced using waste. So again, it allows us to look at different parts of our waste production and how we can use those to ensure that we are being as resource efficient as possible. It can become an export for the UK. Now, this isn't an area that I think is the most important area. It's just a fact, because actually transporting hydrogen is not the easiest thing. Compression is difficult, and actually liquefying hydrogen loses a huge amount of energy. So that's not necessarily the best thing, but it's an option. It uses infinitely recyclable materials like platinum in fuel cells. So this is a material, non-ferrous metal, that can be recycled forever. And there are a lot of other technologies that don't have that option. It allows us to reduce the use of non-recyclable materials and the environmental damage that potentially goes with the extraction of those materials. So it enables, as we said before, greater use of renewables through longer term storage. And at the moment, it's looking like it really is one of the only good storage options for making sure that we maximize the use of our renewables. It allows for better air quality through zero emission vehicles. Now, this is something we're pushing quite hard at the Institution of Mechanical Engineers, because there is a real opportunity to decarbonise much more rapidly using alternative fuels than perhaps using battery electric vehicles, particularly for larger vehicles. Reduced emissions from heating networks, I'm sure a lot of people have been made aware of that much more recently, and small scale generation and decentralization. So these are real opportunities for our regions to have access into the main gas distribution system and produce hydrogen that can be supported through that network, or can be used completely separately for example, refueling trains in certain regions. And then there's a reduced reliance on overseas imports. Now, again, this isn't an anti-globalization issue. It's much more about, as we've seen very recently, when a lockdown like we've had now occurs, that there are opportunities for us to maximize our own assets here. And we should be looking at how we can continue to do that in the future. So in terms of the user experience, I'm sure other people will talk about this a lot more, but to a certain extent, I think if you are not an engineer and you're not working in design, build and servicing and maintenance, your experience may be very similar. There'll be upstream production and transportation. We see that in oil and gas as it is now. There'll be refueling. Again, this is a very familiar activity that happens in petrol stations right across to refueling at ports and at airports. The existing gas infrastructure will be there to allow us to access the 85% of homes through heating that uses gas, and we can reduce the CO2 emissions from that. And as we gradually are able to increase blend, and I'm sure somebody will talk about that, then a reduction in the emissions goes along with that. And then for green hydrogen use in industry. Now, as I mentioned before, this is really important because it's an area where we use a lot of hydrogen in terms of petroleum refining, which will reduce, but also in the manufacture of food and electronics and obviously fertilizer too, which we're possibly likely to end up using a little bit more of because there are issues with soil. So we have to sort of start to work out how we do this in a much more sustainable way. But there's a short-term opportunity there. And that means that we can begin to build that market. So I just wanted to talk very briefly about innovation. Now, this slide is from a presentation that I gave specifically about heating, so I'm not going to talk too much about technologies, but I wanted to draw attention to the socio-economic elements and the thinking elements around innovation. So in terms of socio-economic, the creation and expansion of markets, as I just talked about, is something that has been a struggle for hydrogen for a long time. I mean, from when I first started studying it, what goes first? Do you produce the hydrogen? Can you produce enough of it, or do you use the hydrogen? How do you do it? And we're still struggling with that today. We need to look at how building regulations work. There's a lot of work going on in the background around safety for appliances, for other aspects of our lives using hydrogen. how do we manage an incident in a tunnel, for example, if you've got a train that runs on hydrogen? There's all sorts of work going on in the background. Today, along with some colleagues of mine, we've launched the Levelling the Playing Fields in Policy. So working with Chris Jackson at Protium and members of the hydrogen industry, we have identified a number of anomalies within policy that means that hydrogen is actually disadvantaged in terms of a decarbonisation tool. So there's lots of aspects around that where we need to innovate a little bit more. And then I think one of the most transformative areas is in our thinking. We spend a lot of time, as was mentioned earlier, saying this is the solution to decarbonising our global industries. No, this is the solution. And you just end up in these running arguments with each other that never result in the actual production of any infrastructure or any plant, and we don't actually move forward. Our population is going to continue to increase. We need to make sure that we have in place systems that will allow us to live in a much more sustainable way. So we need to get out of our own way and out of each other's way and support each other in the shared goal of actually decarbonising, because that is a shared goal, and everything, as mentioned, all of the infrastructure is going to be required. So then just finally a quick slide that shows some of the various reports on hydrogen. I've written quite a few of these. I've been involved in writing quite a few of them, and I was very privileged to ask to review the hydrogen guide that's just been produced by the Energy Institute. But what I would say is we need to start to have a little bit of faith about what's in all of these reports, and actually start to deliver new infrastructure. So again, it's a kind of call to action to let's start moving forward and have a bit of trust in each other and trust in all of the research and work that we've done. So that's it from me, and I will hand back to Steve.
Thank you very much, Jennifer. Thank you. Now we've got Adam from Northern Gas Networks, who's going to take us through what's going on up north in terms of the pilot and the plans, and talk particularly about the aspects of heating and cooking. Adam, good afternoon.
Good afternoon. Good afternoon, everyone. As Steve said, my name's Adam Madgett. I work for Northern Gas Networks, and over the past few years, I've been heavily involved with the High Deploy project, as well as some other innovation projects in NGN. And today, I'm just going to give a brief overview of some of the projects that we are working on and looking at how we can bring hydrogen into homes in the UK. So just briefly, for those of you that don't know, Northern Gas Networks, we're one of the 4 gas distribution networks in the UK, based in the north, as the name suggests. The other networks comprise of SGN, Cadent and Wales and the West utilities. So just a brief bit of background before I get into it. The gas networks we've been working on exploring how we can use hydrogen to heat our homes since around 2013. And it's really the past few years we've really started to see some real momentum, and the projects like High Deploy are delivering some real tangible results. And when we talk about hydrogen, we talk about 2 different approaches. So we have blending up to 20%, which is projects like High Deploy and HyNet, and the other avenue, which is 100% hydrogen, which is looking at projects like SGN's H100 and NGN's H21 projects. Now, in addition to that, we've also got support from government in their High for Heat programme, which is a BASE project which focuses on 100% hydrogen downstream of the meter. So as gas distribution networks, we are responsible for all the pipe work up to the customer's meter, and downstream it's obviously within other areas of the industry, and that focuses on the High for Heat programme. And most recently, a project that was launched by the ENA called Gas Goes Green looks at how we can demonstrate introducing green gases like biomethane and hydrogen that can produce a carbon neutral gas network by around 2045. So I'm just going to move on to a few of these projects, but before I do, it's worth, I suppose, setting the scene for the people out there watching this webinar. I know there's a few people that have probably seen this slide before, or this graph essentially. But as you can see from the graph, heat contributes to a significant amount of carbon emissions in the UK. And unlike the electricity sector, where they've made good progress in decarbonising, The same can't be said for heat. So this is why networks like Northern Gas Networks are investigating how we can decarbonise this issue. And in addition to that, we've also, there is support out there from the likes of the Committee on Climate Change, who advise government on their carbon policy, which identified that hydrogen is a real necessity in reducing our carbon emissions, and that grid blending is an enabling role in that transition to using 100% hydrogen. So just briefly on HydDeploy, it's a program which is focused on demonstrating the safety case for 20% hydrogen in the existing gas networks. It's split over 3 phases. Phase 1 is taking place right now at Keele University in Stoke, where we are blending in around 101 residential properties. Phase 2 is a public trial in the northeast in our network, where we are blended. Well, we aim to be blended in around 668 properties, and then phase 3 is a further public trial within Cadence network. So as I mentioned, we are down at Keele at the moment, and we are blending. And to get to that point, there was a significant amount of work that the project team put together, allow us to progress towards that significant milestone of injecting hydrogen into the network. I mean, for example, we carried out extensive testing on the types of materials that were on the Keele network. We looked at the gas characteristics and how it might change with a blend. We also carried out extensive customer engagement with the customers involved with the trial and not involved with the trial, to see what their views might be in using this new green source of gas in their properties. But I suppose one of the final points, or one of the key areas that we looked at, was how appliances might perform differently with an increased amount of hydrogen in the gas stream. And it's really obviously quite a poignant topic for today. And really, I suppose what I'm here to say is that the outcome of that research on the appliances side is really quite boring. And when I say that, the customers don't need to change a thing. The appliances, their cookers, their boilers will operate the same as they do now on natural gas, as they will with up to 20% hydrogen. And just a picture that I've got on the slide here is an extra piece of work that we commissioned down at Keele, where we've got 4 pairs of boilers from the leading boiler manufacturers in the UK. One is operating on a blend, and one is operating on natural gas. At the end of the trial, we're going to hand them back to the suppliers to see if it's had any, if they can tell what effect that has had on their boiler, and we don't anticipate anything coming out from that. So just in terms of timelines, we started the project in 2017. We're looking to finish by 2023 with the second public trial, and when we get to that point in 2023, we as networks would be comfortable to say that from a safety and operational perspective, there wouldn't be any barriers in rolling out hydrogen across the UK. There may be some other work in terms of the commercial arrangement that would need in terms of stimulating a hydrogen economy, like we've had, for example, the renewable heat incentive, which was used for biomethane injection. I mean, the blending benefits are quite clear in terms of, it's easy for customers. They haven't got to change anything in the way that they currently heat and cook their homes. There's significant carbon savings in that, the equivalent of 2.5 million cars being taken off the road if it was rolled out across the UK. And it allows us to build up evidence to move forward to that transition to 100% hydrogen in the future. And just briefly, another one of our projects that we're involved with is the H101 project, which is focusing on 100% hydrogen, as I discussed earlier. This is being led by NGN in partnership with the rest of the gas distribution networks, and is currently split over 2 different phases. Phase 1A is taking place at the HSE's site in Buxton, and Phase 1B has taken place in DNVGL site up in Cumbria, in a test site in Cumbria. So just going into them in a bit more detail, the background testing was all around about existing assets in our ground, taking them from our network and testing them at the HSE site to see how they might the leakage rates compared to natural gas on them existing assets. So testing them on natural gas and then testing on 100% hydrogen. And there's been some positive results to date in that the assets that leaked on natural gas leaked on hydrogen, and the ones that didn't leak on natural gas didn't leak on hydrogen. I know that's quite vague, but the results are being analysed at the moment, and they'll be due to be published in the near future. Phase 1B is all around the consequence testing. So if there was a leak, what would happen, and what would how the gas might behave differently. So we take that learning from phase 1A and apply it into phase 1B. And again, these results are currently being analysed and will be published in the near future with phase 1 results. As I touched on, it's quite a key point is around the social side of the social sciences side of introducing a gas like hydrogen. A separate piece of work the project undertook was the social sciences work, and there were some key findings from this in that what customers highlighted from this project is that they didn't consider safety as a barrier for acceptance. They trusted that the networks would be doing the right thing for customers. However, as you can imagine, disruption were barriers, and this is work that we're looking to explore furthermore in future phases of the work. I think one of the key facts or outcomes from the project is, and it won't surprise you, is that customers want to be told the facts. They want to be told what's going on, and they want to become brought along on the journey. And as I think, as we all agree, that's the most sensible approach to get us towards this decarbonisation future of using hydrogen. Further on, there's a next phase for H21, and this is really building the stepping stone to the next step of providing evidence that will underpin any future work for us to move forward to a public or a community trial, prior to conversion, similar to what we did with Towns gas to natural gas. And just briefly, there's the different phases in this next piece of work are looking at the network operations and how might our operatives operate differently on 100% hydrogen. What do we need to change within our procedures and practices? An unoccupied trial. So once we've identified what we need to do differently with our procedures, how might we go about actually doing that? And then a combined quantitative risk assessment to look at comparing how safe it would be on 100% hydrogen, and also, as I mentioned earlier, a further piece on social sciences. So just briefly I'll just briefly go over. So for the High for Heat program, this is, as I mentioned, this is a BASE project which is focusing on downstreaming the meter, and there's various work packages in this project which are really supporting the networks working in looking at 100% hydrogen, and it ranges from different work packages from new appliances to the potential for industrial uses of hydrogen. So I think you can see with the network and the government working together, there is a joined up effort and approach to how we could look to use this as a potential low carbon source of gas in the future. And one thing that is key to this is that, as I mentioned earlier, we do need industry to come along with us. And the facts are clear that industry is responding. And for example, we've got Worcester Bosch's hydrogen ready boiler that they launched this year, and I know Baxi are carrying out innovation in this area as well. And most recently, we had the Hydrogen Task Force, which was created in March 2020, which really sets out the role of hydrogen in delivering net zero. So there is that supply chain focus as well within this approach to 100% hydrogen. Oh. Sorry, having a bit of technical difficulty here. There we go. Right. So just a brief summary of what we're looking at. So in terms of what the networks are doing, there's a number of programs that are exploring the use of hydrogen in our homes. Blending, we really see as the first step in reducing carbon emissions. Well, we haven't got to make any changes to customers' appliances or their behaviour, and we can build on that and use that to focus on 100% hydrogen in the future. As I mentioned, the recent Gas Goes Green study actually showed that the investment in hydrogen infrastructure today could deliver net savings of £89 billion by 2045. And that is ahead of, obviously, the 5-year target of being carbon neutral by 2050. I think one of the most important things that I'll leave today is that we are focusing heavily on the customer side of this work, and we understand that without their support, it makes things more challenging, and we need to bring them along on the journey as they have described to us. That's it from me today. I'll hand back over to Steve. Thank you.
Thanks. Thank you, Adam. That's a really, really good sort of, I think, expose of what's going on, which has been going on, you say, for quite a while, but I think an awful lot of people probably aren't aware of some of those details. So thank you for that. For anyone who joined this webinar slightly late, can I just let you know, if you have a question, please just put it in the chat and we'll pick them up afterwards. If the question is particularly aimed at any one of the speakers, if you could just note their name at the end of the question, that will help me make sure it goes to the right person, but thank you. Okay, so our next speaker is Chris Jackson, and over to you, Chris. You are on mute, Chris. Chris, you're still muted. That's it, got you.
Oh, you can hear me now?
Yep, over to you, Chris.
Wonderful, thank you. Locked out for a second there. Hello, everybody. Hi. Today, I'm my task here today is to demystify the use of hydrogen in the as an energy storage medium or an energy transport medium from renewable energy. So my experience is 23 years in hydrogen and fuel cell systems. So that's development of fuel cells, steam methane reformers, integration with renewables, and infrastructure in a number of different places around the globe. Well, having a technical challenge moving the slides, unfortunately. There we are. So the first thing to say is that we have seen some significant changes over a very short period of time with respect to our energy mix. So in terms of renewables coming into our grid mix, we can see that as we've put a significant the diagram in the top right shows how we have since 2012 more or less phased out coal, which is a particularly polluting form of energy, and
we were doing really well. The technology was working for us. I seem to have lost Chris temporarily. I'm going to give him 1 minute to come back on. If not, then we'll move on and then come back to Chris when he manages to reconnect. So stand by, Mike, because I might be coming to you sooner than you otherwise would have thought. Okay, Mike. Right. Okay, that's on my stopwatch. Right. So it means Mike will do head of business development at Alstom. Thank you very much for moving the slide. So we can go to you, Mike, and then we'll try and come back to Chris afterwards. So thanks, Mike. Over to you.
Well, thank you very much. Hopefully I won't suffer similar glitches, but we will see how that goes. So yeah, I'm from Alstom, and Alstom is not or it used to be a name in the energy sector. We are now specialists in sustainable mobility. Sustainable and smart transport is what we do. In particular, well known for what we do in terms of rail transport and rail mass transit systems. So today we're going to have a little think about hydrogen use in transport. We've had some very useful scene setting already. And I also want to look at the user experience. Now, clearly, I'll do this a little bit from the train and rail perspective, but many of the points are applicable across the transport sector. So please don't panic if you're not a train spotter. So in theory, I have control. Yes, there we go. So hydrogen-powered transport. We've talked a little bit about why hydrogen now has its place in the energy scene. So why are we seeing people also rushing towards it for transport purposes? What's it about? You know, we've got huge global multinational businesses like Toyota, Hyundai, Honda producing already hydrogen-powered cars using fuel cell technology. We as Alstom have put the world's first hydrogen fuel cell trains into passenger service. Corradia Island has been operating for now best part of 2 years and is a well-proven technology. Lorries are coming, HGVs are coming. We've got international businesses like Bosch and Cummins buying into the supply chain, getting involved in fuel cell production. And obviously in China, we're seeing a big shift in investment from the battery sector across to hydrogen and fuel cells. So why is everyone doing this? Why does it fit for transport? And in particular, why is Alstom looking at hydrogen trains? I'm still mystified as to which button made that work. That's gone too far now. So the reason is what Jen mentioned, and I think Steve said even in his introduction, it's about storing energy. So if we want to move anything, we need to use energy. And apologies in advance, Jen, I'm not an engineer or an IMECI expert, so excuse my use of the phrases here, but fundamentally it takes energy to move anything. On the railway network, we have a brilliant solution to a low emission movement of vehicles. It's called electrification. You'll all have heard of rail electrification and its pros and cons, but like with the point that Jen made initially, electrification is key to creating a decarbonised railway. And if we're going to get to net zero in 2050, a decarbonised railway is key to our transport infrastructure. So, however, we find ourselves currently with roughly 40% of the UK rail network electrified, even just 25% in Scotland, for example. So we have huge areas of the network that are not electrified. And whilst we could get cracking and electrify them, and Alstom provides electrification, we in fact provide all of these solutions that I'll talk about. There is clearly a need for a range of solutions and a range of options. And what we do need in the industry are zero emission self-powered trains, is what we might call them. So those are trains that haven't got a wire or a third rail to conveniently pick up the energy through. They are trains that have to take it with them. And traditionally, we've always used diesel for that. And let's face it, it's a fantastic energy store. It's very flexible to carry, it's very energy dense, and from that point of view, it is the sort of perfect solution for rail traction and road traction, apart from the things that we've become very much more aware of over the last few years in terms of clean air emissions and carbon emissions and the impact they're having on the health and well-being of both people and of the planet. So, but if we look at relative energy density, diesel is 35.8 megajoules per litre. A similar comparison for hydrogen is 4.6 megajoules, so about 8 times less efficient in terms of its energy density per litre volume. So, and that's when it's compressed to 350 bar. And batteries are another halving of that ratio. So we are, when we're looking at how we can carry our alternative energy, we are trying to find something that gets us as close to diesel as possible. And with current technology, hydrogen is the best solution that we have found. The road sector uses a higher pressure of storage for hydrogen. They store at 700 bar, so they get a slightly better energy density. But for commercial vehicles, rail vehicles, and other heavy-duty vehicles, 350 bar has been chosen as the standard sort of compression rate. But needing 8 times the space of our diesel fuel tanks is obviously a constraint and a challenge to the design of the new vehicles that are going to come forward. And with batteries, that constraint is merely amplified. And we also have the issue there with the weight associated with battery systems. That's not to say that batteries are not relevant or appropriate in certain applications. And again, I go back to tribalism. Please don't anyone interpret me talking here about hydrogen to mean that we wouldn't talk about battery trains or combined solutions of these technologies. And in fact, the most of the vehicles that use fuel cells also use batteries, because if we go back to the very fundamentals here, the more efficient you can make your energy system, the less energy you need to carry. If we can recapture braking energy and other forms of waste energy, we are in a place where we can actually reduce our overall consumption, which helps with our ability to travel further on the same amount of energy. So if those are the reasons why we're using it, today's discussion is around what's the user experience. And again, my thunder's been stolen slightly because, as Jen pointed out, it's pretty much the same. So if we could do a hands up, and I can't see you all, but if we were in a room doing a traditional kind of seminar, I'd say hands up who's been on an electric train. And I bet you about 90% of the room, if not the whole, all of you would say, I have. And a hydrogen train is fundamentally an electric train. So that means it's quiet, it's clean, it's efficient. It's certainly, and compared to a diesel, it has a smoother ride and none of those attributes that we associate with even the best installations of diesel engines around vibration and noise and what have you. So from that point of view, the user experience for a customer or a passenger on a train is very, very familiar. But I have identified here that I'm talking here about the one particular type of user, and any system has potentially multiple users. So while we look at the passenger experience, a hydrogen train is like a new electric train. So you get your facilities, you get comfort, you get Wi-Fi, you can have everything that today's 21st century train should provide. And exactly the same, of course, applies to other modes of transport. A Toyota Mirai will feel like driving any other car, arguably any other electric car, but if you've driven a Mirai or an electric vehicle, you know it's not a million miles dissociated from driving a regular automatic transmission car. You just press and go and you press to stop. And as long as you remember to steer in the meantime, you should get to where you want to be. And the trains are very similar. It's not a massive shock. And in fact, when people rode the German train, the one on the left there, I was on the very first trip that it ever took in passenger service, and in the end we had to put signs up to tell people what it was, because no one really understood what the difference was and why it was blue and everyone was making a fuss about it, and why were they being interviewed by journalists on the journey. It's in some ways disappointingly underwhelming, but practically speaking, it's a that's what you want. We don't want shock and awe, and we don't want barriers to people adopting these things. So I'm trying to jump on to the next slide. There we go. So who are the other users of trains? Well, from our point of view, a key user of a train is actually the operator. Now, if you're a car driver, you are the operator and the customer because you own it and you drive it. But in the train world, the operator is a different organisation. They're the people you buy your ticket from, and they're the people that move the train from A to B. And from their point of view, there's a different set of user experiences. Obviously, they want their passengers on board to be satisfied and comfortable and safe, and they get that. But they also get the benefits of zero emissions in stations and in their depots. That means those passengers are not exposed to potentially harmful emissions anywhere along their journey, even in the station with a roof. It also means that their staff can work on a cleaner, more a cleaner environment, less need for the types of controls that are necessary in a diesel working environment. They also get all-weather performance. Now, of course, with diesel, that's taken for granted largely. All vehicles, and diesel is not immune from this, can suffer in cold weather, but the hydrogen train is an all-weather vehicle. It doesn't have a significant performance reduction because of the cold, and it can offer in current form a range in excess of 1,000 kilometers and speeds of up to 160 kilometers per hour. Now, of course, you can always play tunes with those numbers. If you want to do 200 kilometers an hour, you could, but if you chose to do that, you might go less distance, which is probably why most Teslas travel in the slow lane, not the fast lane of the motorway, even though they're eminently capable of blitzing anything else on the road. So you set your aspirations correctly. You can operate a full day's service without refueling midway, and you can replace the vast majority of diesel trains on the world's networks with those performance parameters. So when you get your trains back to the depot at night, you refuel them. And as we've seen in the automotive sector, there's a great deal of excitement around the fact that refueling a hydrogen vehicle is very, very similar to refueling a diesel or petrol vehicle. Time to refuel and the process of hooking up a pump is familiar and simple, and again, avoids any of those sort of shock of the new type impacts, and also gets around some of the problems we've seen with attempting to create the electrical support infrastructure necessary for multiple charging and parallel charging of fleets of vehicles in a single place. And like I said earlier, the maintenance environment is cleaner. You don't have the risks of ground pollution and other factors that could be relevant. And then we even have a third user. Again, I'm going to try and get it. There we go. And in the rail sector, that is the infrastructure owner. The organisation we know and love in Britain is Network Rail, but they are a key player in all of this. And again, this is analogous with other forms of transport. So if you happen to be in the road sector and you are one of the oil companies currently delivering fuel at fuel stations, you've got a vested interest in the infrastructure around whatever the system the vehicle uses. In our case, electrification, whilst indisputably appropriate for certain high trafficked and high speed routes where energy consumption is high, but returns are also high, the type of effort that goes into electrifying a route is justifiable and relevant. However, if you don't have to electrify, then you don't have to risk the service disruption that it can present, and you are able to introduce a new technology in a lower risk manner that can have its attractions. That's a user feature that's a benefit. And it allows you also to focus on what it is that you, where you think the right technology should be applied. So an infrastructure owner like Network Rail can determine where it's necessary to electrify, and where electrification isn't applied, it knows that there are alternative solutions. New fueling facilities will be required, of course, for hydrogen, and the rail network is a network of fueling facilities for diesel trains, and they will need over time to be translated into other forms of fueling provision, and that does mean some unfamiliarity to the infrastructure owner, so that the user experience there is a little different. Instead of dealing with fuel storage tanks and other factors, we have then the need to put tanks and other handle compressed gas. That's going to take some getting used to, of course. But once the network of refueling is there across the UK, a hydrogen train becomes a go anywhere train. it can move across the nation in the same way that diesels do, and is a very logical replacement for that. And again, back to the chicken and egg phenomenon that was mentioned earlier, do you provide fuel stations before you provide the vehicles to use the fuel, or do you provide the vehicles that then create the demand for the fuel station? In the case of captive rail fleets, you provide both at the same time. And slowly but steadily, you can build up a network across the nation. That's harder to do with individual consumers in their cars, but from a transport perspective, with HGVs and with taxis, buses, and trains, there is the potential to build around captive fleet deployments, which is a very exciting development. So finally, really, for the UK, we do have currently a proposed product, which is a converted train, which would be used and is available now, market ready. It needs to go through obviously its first deployment and appropriate approvals to be deployed. But we are at the point in the industry to be able to offer hydrogen technology in the rail network as of today, and that would take 3 to 4 years to bring into passenger service. But it's at that state of readiness. Thank you.
Thank you very much, Mike. Thank you for that. And the good news, everybody, is we've got Chris back, but without the video. I think he dropped off. So to be safe, I think you're just going to be on voice, Chris, and working your slides. So we'll go back to you, and there we are. Back. So your first slide is now up, Chris.
Beautiful, thank you. And can I just confirm that you can hear me?
Yes, can hear you fine, thanks.
Lovely. Right, sorry for that, everyone. So I am back. So where were we? We were busy demystifying renewable energy and hydrogen as a storage medium for that. So there we are. Okay, so yes, we've very rapidly decarbonized our grid mix. Carbon has almost been completely phased out. Renewable energy is coming into a significant percentage, a very tangible percentage, and that is mainly through contracts for difference, which is support for procurement of renewable energy over long periods of time, which de-risks the process and protects the supplier and the user in terms of the cost of that electricity. The net result of this is that the cost of renewable energy is falling, and the rollout continues. The challenge that creates is the constraints in our transmission network for electricity. So we have constraints which lead to curtailment, and curtailment is where the generator is asked to either turn down or turn off their production assets. So namely wind turbines in the examples that I'll be showing. Now that has a cost because the operator then has to pay the renewable asset owner a fee for that, and you can see in the bottom left-hand corner here that those fees can be quite significant. And over the last, say, 10 years of operation of renewables, that's resulted in just over £6.5 million in curtailment payments. So, sorry, 650 million pounds in curtailment payments. So, as the rollout of renewables progresses, as has been announced by the government, what that means is significantly more wind and solar will need to be rolled out to meet our commitments. But alongside that, significant challenges in the network will exist, and technologies are required in order to balance out the constraint issues and indeed remove them by routing the electricity which would otherwise be lost into other applications, one of which can be the production of hydrogen at very large scales. And the key point on this slide is that there are a number of other countries with significant challenges in this respect. So the UK has by no means the largest challenge in terms of curtailment and restriction in the network. So quite often when we talk about hydrogen, there's a discussion that results around battery or other energy storage solutions versus hydrogen. And really, that is only really a question at comparatively small scales. So when we're talking about balancing the network, the diagram on the left shows just how significant the difference is between hydrogen as a storage media, chemical storage media, is, and the potential for batteries. They serve basically different markets or different areas of the market at really quite different scales. And therefore, if we look to the diagram on the right, in terms of the decarbonisation of industry, hydrogen is one of very few practical solutions in order to be able to do this. So in terms of the constraints that we've talked about, and in terms of the decarbonisation of industry and the balancing of the network, hydrogen provides a very good fit for all of these challenges that our future network faces. In talking about hydrogen, when it's used in this way, it's good to clarify the difference. So it's quite often referred to in a number of different ways. It's quite likely that you will hear the terms grey hydrogen, blue hydrogen, and green hydrogen. They're basically defined in the following way. Grey hydrogen is the hydrogen that we have today. So that hydrogen is generally used industrially. It's generally generated on chemical sites where it is, where it's used, and that's in reasonably significant volumes. But it's generated from steam methane reformation, and generally that does result in carbon dioxide emissions. So that form of hydrogen production is termed grey hydrogen. The carbon emissions can, however, be captured, and when they're captured, some of the other projects mentioned H21 earlier as an example, when that carbon dioxide is captured, it can either be used, so it can be converted into other chemicals, or at a much larger scale, it can be deposited into under subsea or underground onshore caverns. And there are a number of different areas that can be done, from the top of the country to the bottom, and indeed globally. And there is, there's significant work globally in the area of carbon capture to be able to produce blue hydrogen. Another way of producing hydrogen is to split water. So as many of you probably know, water, it consists of hydrogen and oxygen. And if we apply an appropriate voltage to that, we can separate the two of those electrochemically. So hydrogen and oxygen can be separated. And when we do this with general grid mix electricity, that would also be termed grey. But the grid mix, as we've seen on the previous slides, is greening. So we're transitioning towards green hydrogen, even if we use grid-based electricity. In addition to that, if we use renewables straight to the electrolyzer, so co-located or transported, then we can also term that green hydrogen, and that is a significant opportunity for the renewables industry. A quick word on electrolyzers to ensure that everybody is familiar with what we're talking about. Electrolyzers, as I mentioned, and as you can see in the top central diagram, is the splitting of water into oxygen and hydrogen. That has been an industrial process since the 1930s. So in the bottom of this, in the middle bottom slide here, we can see banks of electrolyzers generating 30,000 normal meters cubed per hour, which is a hydrogen generation at a significant size. And that was in the 1930s. That technology was generally alkaline based, or that technology was alkaline based, but now we have more options in terms of electrolysis. So we have what's called proton exchange membrane electrolysis, or PEM electrolysis. And And in addition, while I have two chemistries written on the slide here, there are actually three. A far more common form, which is under development, is solid oxide electrolyzers. Fundamentally, all of those technologies can separate water into hydrogen and oxygen. And you can see a modern example of that in the top right-hand corner, and the approximate size of a 3 megawatt system. So that's able to generate just over, well, between 1.2 and 1.4 tons per day of hydrogen. So you can see that next to a human being. The benefits of electrolysis are that they can ramp up for renewables, are that they can be ramped up and ramped down, so they can respond to the changes in demand or production on the grid. They can operate in a range of different environments. So industrially, this technology is used from Saudi Arabia to Siberia. So there are thousands of systems deployed globally. The most modern form, or the more modern form of electrolysis, which we just chatted about, PEM, that is able to respond to the grid more quickly, and therefore is able to balance the grid potentially more effectively than the alkaline technology. However, both are currently in use for this purpose, and demonstrated in a number of trials. Some of those trials now, globally, there are many trials and many different examples. I've selected here, just in terms of the demystification remit, to choose one location, which is Orkney, an archipelago off the northeast of Scotland. And I just wanted to mention a couple of the applications that have been trialed there using renewables. So High Flyer is a project which looks at the use of renewably generated hydrogen as an aircraft fuel. High Spirits looks at the fuel switching to provide heat in terms of the distillation of gin. Big Hit was a project which used renewable energy to provide hydrogen for heating in schools and to transport around the islands. For use in transport. Surf and Turf was a project which demonstrated the first use of tidally produced hydrogen globally, the first use of tidal hydrogen. High Seas considers the use of hydrogen in shipping. We've got the use of hydrogen here in HyDime. We've got the use of hydrogen in internal combustion engines in driven vehicles. What else do we have? Sea Fuel, which considers the conversion of seawater into hydrogen fuel. So you can see the number of demonstrations and the breadth of different applications goes on and on. In addition to that, I've just been moved forward.
Yeah, if you can draw us to a close, Chris, please.
Yep, certainly. In addition to that, we have, in addition to that, the current project's under discussion. So I've shown a wide range of different applications. The wind, some of the largest wind companies in the world and the oil and gas companies are partnering together to demonstrate the use of offshore assets, so wind and the repurposing of oil platforms in order to generate significant scales of hydrogen at sea, and then bring that back either as a mixture with the gas currently generated or for use in 100% hydrogen pipelines back to the shore for industrial use. There are a number of these projects coming through. There's 3 mentioned on the slide, but there are many. The production of hydrogen and the transportation of hydrogen are of course linked, and there are, as Jen mentioned earlier, a number of different ways of moving hydrogen. So currently we commonly see it as a compressed gas, but we can, and as some of the other presenters have demonstrated, this can also be done blended with methane in pipelines. but there are other options. So hydrogen could be moved as liquid ammonia or liquid organic hydrogen carriers as well. So the first of which, ammonia, is a globally transported material largely used in the fertilizer industry. So there is already standards for moving this around the globe. And in terms of organic hydrogen carriers, these are materials that can absorb hydrogen into effectively a heat transfer oil, so widely used in industry, and it can move hydrogen from the source of production to the area of use and then release the hydrogen for use as a gas. A few words to say on this are that the marine industry has given significant backing to the use of hydrogen for their own fuel and for transport. Yes.
Okay.
Thank you.
Thanks, thanks, Chris. Sorry to cut you off, but I do want to leave some time for the Q&As here. So,
no problem.
Thank you very much. I've got a load of questions in here that cover, unsurprisingly, from costs to technology, carbon footprint, etc., etc. So let me, in no particular order, just start. Actually, Adam, perhaps there's a couple of questions here that probably get back to you. In terms, you actually mentioned during your presentation that there's going to be some results that are coming out of the trial. How are those results going to get published?
So in the two different projects, so with reference to H21, because I've seen some of the questions on that, that the reports will be published with Ofgem. It's an Ofgem funded project, so it's a network innovation competition project, and we are duty obliged to share any learning that we've gained. So they'll be published through that route. And with regards to high deploy, some of the technical papers and work that's been carried out, the aim, especially for the next piece of work that we've carried out, the aim for that is to be published on RGM's documentaries on their website, so it can be accessed by anyone. But that will be, later on this year, and similar with the H1M project, that will be later on this year. I can, if we do send any communications out to the people that attended, I can attach copies of the website addresses where more information on this can be found.
Right. All right. Thanks so much. I think that information on leakage that you said interests a lot of people, actually. So the ability for people to actually dig into that, I think, is something that's coming through here. Why I've got you, I'll just stick on you if I can for a second. There's a question here from Eugene Price that says, "Isn't the long-term plan not to remove gas from domestic heat and cooking altogether, rather than mix it up?"
I mean, it's certainly not from a network perspective. We've got this fantastic infrastructure in the ground that we've demonstrated for many years can be a safe, reliable source of energy for customers. And rather than doing away with that, we see the possibilities with using transporting hydrogen to replace the natural gas source that is in customers' home as well. And as we've discussed, and has been the theme, it's a combination of the electrification of heat, as well as replacing natural gas with 100% hydrogen that we're looking to focus on. And the networks believe that we've got a roadmap that can take us there.
Yeah. Okay. I mean, just to add to that, and when you think about converting onto electricity, of course, let's not forget that the energy consumption on heat is 4 times the current electricity consumption. So it's an awful lot of power if we're going to use pure electricity. So that's why there's so much work going on thinking about the networks and hydrogen. I'm not sure whether Jen, maybe you could start with this question. What would the cost of CO2 need to be, do you know, which to really incentivize the shift from blue hydrogen to green hydrogen? Do you know what that number is?
No, so I'm not an expert on the the pricing and what it needs to be to make a big difference in terms of actually switching from one to another. I think some of those incentives may actually end up coming from industry a little bit more than they may from your traditional, perhaps, electricity and gas industries, but there may be other people on the panel who have got a bit more insight into the financial side of things.
Anyone want to put their hand up if I don't see it? Nope. Okay. Let me. Well, I've got you, Jen, because as you did your thesis on this such a long time ago, a resident expert here. How does steam methane reformation actually stack up today against electrolysis from a pure cost perspective?
I think at the moment, it's a slightly different way of doing it, and because it does, so steam methane reforming is less efficient than autothermal reforming. If you're talking about stacking up of costs, it depends what you include in those costs, because in order to do that in a way that we would consider to be acceptable and moving across the spectrum of colours towards blue, it would have to have CCS connected to it, and at the moment we don't have a situation apart from a very small scale where that is included. So whereas nearly all new electrolysis is starting from a position of either being greened by the electricity system or being green in the first place.
Sure. Okay. I mean, yes. So it's apples and pears, is what you're saying. But if you do the apples and pears for me, if you just take a non-CCS steam reform versus electrolysis, what's the cost differential?
I don't know. As I'm not a builder of sites, I don't know the difference. I don't know. Adam may have a slightly better insight into that. I'm not sure.
Well, Chris, do you know the answer to that question?
No, that's not what I can answer, sorry.
But Steve, if I might just make a comment, I think there comes a point where you have to stop making comparisons of that nature. If what we're saying is we are seeking a decarbonised solution, the comparisons have to be what are the alternative decarbonised options, not what is the option. You know, it's a bit like saying is a fuel cell train going to be more expensive than a diesel train or something else like that. In the first instance, yes, but if you want to keep it cheap, then you've got to accept the climate change implications of being cheap.
Yeah, I don't. This person would disagree that they were interested in the cost of differentials there. There's a general question here that that has come in, which is, we talked today about all the opportunities for hydrogen, various sets of usage. Which sector do you see it having? Is it transportation? Is it domestic heat? Is it heavy industry as a fuel? Let's just go around the panel. So I think I probably know your answer, Mike, but let's start with you.
Well, I think transport is the area where you can actually start to do it more readily at this point in time. Adam outlined the process it's necessary to go through for conversion of the heat network, for example, and necessarily that's going to take some time. Whereas if you are able to deploy, like I said, return to base type fleets in the transport sector, be they trains or whatever they are, you have the opportunity there to actually deploy hydrogen consuming vehicles and create the fuel supply for them and reap, relatively speaking, immediate benefits in a way that a sort of consumer connected network hasn't got the luxury of doing. And once you've done that, you're accruing benefit every day that you operate those trains and those buses and those lorries. So you start to benefit the overall position we face in terms of carbon very rapidly. So I think transport is a very good sector to start with.
Yeah. Okay, Jen, what would your response be to that?
I think I'd actually agree. I think the rapid decarbonisation side can happen in transport very quickly, and when you look at how we can use hydrogen to support alternative fuels in vehicles, that's a real opportunity that we're not accessing as much as we could be at the moment. There's been a lot of focus on passenger vehicles rather than larger fleet vehicles, and actually that is an area where I think I would agree with Mike that transport is probably a really good option at the moment.
Okay, Chris, with all those things you're talking about up in the Orkneys, you've got some first-hand experience of different uses.
Yes, absolutely, and hopefully my technology doesn't fail me this time. So there are significant scale users of hydrogen globally already. they understand how to handle the material, and they can operate with it. So co-location of some of the technologies that we're talking about on these sites, powered by renewables, these things are already certainly in feasibility studies, and some of them are already in demonstrations. So we've got steel, we've got refineries, we've got ammonia plants in Australia, all of which are planning or actually actively currently demonstrating or developing the projects to demonstrate hydrogen and or green hydrogen in order to displace fossil fuels in the production of very large scale industrial products. So that's a definite area, because and that provides two benefits. Well, it provides many benefits, but two main ones. The first one is the use of renewables to be able to decarbonize those processes, and also for the working together of industry, renewables, and network buffering. So all three of those need to become quite integrated for the future energy mix as we transition.
Okay, thanks. Adam, I'm going to change the question, if I may, because I think I know your answer to that one anyway, from a bias perspective. But just flip back to gas in the networks and safety. There's a question that's coming here about the deployment without an odorant, as everyone probably knows. I mean, we odorize our natural gas today in terms of leaks, and it's quite hard to get an odorant into something as light as hydrogen. So what's the thinking around odorization?
So, I mean, it's with a blend up to 20%. We've done significant testing, and we've worked it, and we've analysed it, and we're obviously doing the trial now. So there is no issue in terms of odorant with a blend. As rightly has been discussed, is 100% hydrogen is a different matter, but there's different work being undertaken in this area to try and identify a suitable odorant that could be added to provide that stenching agent in the gas that we're all used to be able to get over that issue. So it's something that we're aware of. It's not been tackled at the moment, but it's something that is looked to be undertaken in due course.
Okay, thank you. There were a couple of questions that came in just for the audience on the transportation of hydrogen in liquid form. I think Chris actually covered that. There was a question here about the technology of subsea flexible pipelines for hydrogen. Have you got anything else to add on the subsea pipelines for hydrogen, Chris?
Yes. So, okay. So the modes of transport that I've outlined do include the blending of gas and also the transport of compressed hydrogen. The Energy Institute, interestingly, has a working group which is working with all of the oil and gas companies to look at the repurposing of assets which are already in existence, and what would be needed from new products to be able to be sold into the industry from an oil and gas perspective to transport these. So what I can say is that question is actively being researched, and existing products and existing assets are being assessed currently.
Thanks. Okay. A question from Chris Bear here, which I think probably on the lips of many people. If everyone, and by that I mean governments and industry, got on board, why is it really going to take us until 2045 to have this thing up and running?
Well,
so, go on, Mike.
Go on, Chris.
Okay, so why will it take so long to get it up and running? The rollout, as you've seen, well, on one of my slides, the rollout of the renewable assets will take a reasonable period of time and also requires significant support around it. Now, that industry has grown very rapidly and is very successful. A similar growth and new supply chain and knowledge and support would need to come around the integration of, from a renewables perspective, but this is similar from a heat perspective, would need to come around the use of hydrogen and assist the transition. So it's not a question just of technology readiness. Many of the technologies are ready, and the production at scale, as in the mass production of these technologies, will further drive the cost down. down, but the supply chain, the maintenance and operation skills around all of that, and the integration and the gathering of evidence to demonstrate its safety in use all takes time.
Yeah,
Adam next, and then Mike.
Yeah, and I just, I mean, just to echo that, it's just in terms of you know, the roadmap to 100% hydrogen. It's as Chris said, the technology is there to be able to do it. What we as networks are aiming to prove is that the networks can cope with it and can operate as they can today. What's required then is that source of hydrogen to be able to deliver that carbon saving if it was to be rolled out across the UK. And as we look to do that in large scales, the only current method to do that is through steam methane reforming, and to get the carbon savings that we're aiming to achieve, that would be using carbon capture storage. And the plan, as I've seen it most recently from government, is to try and have only just one of them online in the middle of the 2020s, with a further one scheduled in the 2030s. So the timelines there for that infrastructure to get the hydrogen is probably one of the more the bigger barriers in terms of delivering this by 2045.
Mike, anything to add to that at all?
Yeah, I think I would say, I mean, it sounds terrible, doesn't it? We're all here saying things take time, but things unfortunately do take time. The rail industry has been challenged to decarbonise and to remove diesel from the rail network by 2040. So we've got sort of 19 and a half years. The diesel networks and the diesel trains have been evolving on the rail network for 72 years since the first ones were introduced in the UK. So we're going to replace something that's had 72 years development in 19 years. When you look at it like that, it's not as bad. It's still frustrating to take that time. But if you expand the rail sector to the road sector to the aviation sector, there are some huge challenges, not just in finding the right technology, but in deploying it and removing the old technology in a way that is actually viable and sustainable.
Yes. Steve, it's also worth saying that when we say it will take time to get here, and as the question implied, it'll take time to get here, certain aspects of this won't. So there are areas where there are significant there's significant scale demonstration projects which, once demonstrated, additional modules, the technology is modular in many respects, which can be ramped up to start to displace more and more of the fossil fuels that are used in those processes. So it's actually fair to say that the process has already begun. It will just be a progressive rollout, and some areas will be able to absorb the hydrogen more quickly than others.
Yep. Okay, thank you. Can I just, there's a question here from Abby, actually, which is, with China and Russia and USA actually dominating the current demand, which is a fact that wasn't necessarily made today, which countries are going to play the largest role, you think, in hydrogen? I mean, who's really stealing the march here? Jen, I mean, are you aware of who's ahead of us right now in this game?
I guess it depends how you look at it, but I would say that Germany and the Netherlands in Europe are doing some really good work on this, and they also have similar energy infrastructure to the UK, which helps as a good comparison. If you look really at what the options are in terms of who's got renewable resources, so who's got a lot of sun, who could potentially use this in a way that is maybe different to what they do now. There are the Middle East countries that could potentially change what they do and what their export is. So there are a lot of options. And then, of course, the UK does have some great resources, and particularly I know Scotland are particularly interested in what this means for them in terms of hydrogen production. So there are lots of different countries who may do this at a slightly different pace depending on what they're trying to achieve.
Yeah, I guess that's all linked into industrial strategies. So a question for me to a certain extent, it seems to me, one of the things that we're worried about is our steel industry, which is and our cement industry, for example, huge consumers. So wouldn't it make some sense if we're going to put some incentives in place to actually put some incentives in place for hydrogen production near those and clean those up very quickly?
So there are a number of government-funded projects that have or projects that have been supported by government recently to look at fuel switching for industrial processes, and some of the elements that you mentioned are actually covered there. So the innovation, the integration, the trialing, and the learning is actually also actively underway.
Great, thank you very much for that. Okay, I think I've covered the vast majority of these questions here. Yeah, I think so. I guess there's a question that came in afterwards, which was, wouldn't it be more efficient to provide more renewable energy and electrify home heating and cooking rather than use electricity to make hydrogen? I think Adam covered that off in his talk, and actually, I'll use that as a kind of to help me summarize. I think it goes back to something that I said right at the very beginning in terms of the need for all technologies. And indeed, as Mike said, we need a range of solutions and a range of options. So, I think you used the word tribalism, Mike, actually, which I really liked, that we're never going to get to net zero. And yes, we adopt all of these. The challenge in a policy sense, of course, is just, how much of each is the right answer. But thank you ever so much to the panel for your time and your effort today. Thank you. All the people who are online, particularly for bearing with our technology. Only one glitch, so I think I'll mark that down as a success. So thanks for listening. Thanks for sending in your questions. If I go back to the hydrogen guide, please do have a look at that. Go to energyinstitute.org/hydrogen and take a look for yourself. As I mentioned, there'll be a recording of this webinar. We'll be emailing all the participants, so you've got the link there. And lastly, we're just going to send out a little questionnaire, just to appreciate your feedback about the session. So it's going to pop up in your browser at the end after you leave. If you could take a minute to fill that in, I'd be hugely grateful. I hope you've learned something from today. I certainly have. I think, as I said, hydrogen is part of this future without any question. It's interesting that the 20% hydrogen looks like it's so easy to do. It's kind of surprising. So why don't we just get on with that right now? And I think, there weren't a lot of questions on details of production here, but clearly the costs are an issue here. I think, like a lot of technologies, we know that until you start to scale up, you don't bring the cost down. So some incentives in place and some policies that start to really kickstart this industry will seem to me something that's coming through from both the questions and the panelists. But thanks everyone today. Thank you for your participation, and all stay very safe. Good afternoon.